All right, so now what we're going to talk about is how to solve limits using substitution. This is the easiest way to solve limits, okay? If you're given a limit and you're given the actual function, not just a graph like you were in the graphical section, okay, and you're not just given numerical information. If you're actually given the function and it says the limit as x approaches a number, how are we going to solve these, okay? Now, I've already told you before, you could use a calculator to do these and make a table of values, but that's actually harder than doing what we're doing right here, okay? Now, you're not going to believe me, but you probably have thought of this already while watching all these videos. Basically, the way that you solve these is by simply plugging your number in for x, okay? Because in most cases, as x is approaching an x value, y is approaching the same value that you would get if you just plugged the x value in for x and got a y value, okay? And you might say, well, why didn't we do that from the first place? Mr. Ryan, why are you making this so complicated? Because most of the situations in calculus are not that easy. In most situations in calculus, when you plug this number in for x, you don't get a number, okay? But you always have to start with plugging in before you try something else. So the first step in solving any limit analytically, very first step is always to plug your x approaches number in for x in the problem, okay? So we're just going to put a 3 in here. We're going to do 2 times 3 squared, so 2 times 3 squared minus 5 times 3. Okay, well, 5 times 3, that's 15. 3 squared, that's 9, and 2 times 9 is 18. So we have 18 minus 15, and that is 3. Now, it just so happens, this is a coincidence, that the input value is the same as the output value, okay? But that is very essentially the answer. If you were to do this with a calculator, you would find that if you had here, 3.0 or 3.1, 3.01, and 3.001, that the values, the output values, by plugging those 3 numbers in, are getting very close to 3 as well, okay? All right, so what about this limit down here? The limit as x approaches 5 from the left of this rational function. You're more likely to see rational functions in calculus than you are to see these just regular polynomial functions. But still, the first thing you're going to do is take that 5 and plug it in for x. So we have 5 minus 2 is 3 over 5 plus 1 is 6, so we have 3 over 6, which can be reduced to 1/2. And so the limit of this function as x approaches 5 from the left is equal to 1/2. Okay? Well, why don't you try to do this one on your own then? Why don't you pause it and do this? I just want to warn you, there's a trick in here. There's something wrong with this one. All right, so we're basically just going to plug 4 in for x in both of these. 4 plus 5, that's 9, okay, over 4 minus 4, that's 0. Uh-oh, stop. Some of you are going to want to say that the answer to this is 0. It is not. Remember from your pre-calculus that anytime you have a number, a not zero number, divided by 0, that's a vertical asymptote. Okay, this is not a real number. This is undefined. And therefore, we do not have a real answer to this. And what that basically means, here's a situation where we would say that the limit does not exist. Anytime you get a non-zero number over 0 as an answer for your limit, you're just going to put does not exist, because it's either infinity or negative infinity. Now, you can find out whether it's infinity or negative infinity by doing a table problem, okay? All right, so that's it for the beginning of substitution. What we're now going to do is we're now going to learn how to do what are called piecewise functions. And when we do one-sided limits with piecewise functions, we can do both the left side and the right side of the number, but we're going to wind up plugging the number, substituting the number into a different expression for the left side or the right side. All right, so what we're going to do here is we're going to start dealing with piecewise functions. Now, I don't know how much experience that you have with piecewise functions, but a piecewise function is very similar to what you saw in the last segment, where we had that graph that had all kinds of weird breaks and stuff in it. That was a piecewise function. Okay, this is also a piecewise function. What this is saying here is that the function f of x is defined by 2 expressions but for different x values. It's still a function, okay? It doesn't break the vertical line test, okay? What it's saying here is that if you were to plug in the number 2, because this says when x is less than or equal to 2, okay? So if you were to plug 2 into this function, you would plug it into this up here. If you were to plug in a number less than 2, like 0 or -5 or 1, then you would plug it into this piece right here. But do you see down here where it says when x is greater than 2, then this is the function. So if you're going to plug in a number larger than 2, like 3, 4, or 5, or 100, or 1,000, or 732, you would plug it into this piece of the function down here, okay? So piecewise functions are conditional. They depend on what x value are you plugging in. Oh, you're plugging in a number less than 2? Plug it in here. Oh, you're plugging in a number larger than 2? Oh, plug it in here, okay? And this is now going to matter, because if we're going to do a limit of f of x as x approaches 2 from the left, all of these numbers are going to be smaller than 2. You know, if we made a table of values, all those numbers would be smaller than 2. So to solve this, we're just going to plug in 2, but we're going to plug it in to the piece where it's smaller than 2. So to find the answer to the as x approaches 2 from the left, we're going to plug this number, because we're using substitution. We're just going to substitute in the number 2 in to the function f of x in the piece that has all the numbers that are less than 2. Well, here's the less than 2 piece, so just put a 2 in here. 2 squared is 4, plus 3 times 2 is 6, minus 5, 4 plus 6, that's 10, minus 5 is 5. So the answer to this limit is 5, okay? All right, well, what about the other side? Well, this says what is the limit of f of x as x approaches 2 from the right? So we want all the numbers that are larger than 2. Well, for numbers that are larger than 2, we're going to use this piece right here. So we're going to plug this number, 2, in for x's here and here. So we're going to have 3 to the second power, or 3 squared, that's 9, minus 2. Well, 9 minus 2, that's 7. So the answer to this limit is 7. And here's a great situation where the answers to the left side of a number versus the right side of a number are different answers, okay? We're going to do one more example of these. I'm going to let you try it on your own, and then we're going to call it quits. All right, so this piecewise function is just a little crazier, okay? This piecewise function actually has 3 parts to it, and it depends on what your x value is. So what this piecewise function is saying is that if the x value you're plugging in is less than -5, then you're going to plug it into this piece, the x plus 3. But if the x value you're plugging in is larger than -5, but less than 3, so any number between -5 and 3, you're going to plug it into x squared minus 11. Lastly, if you were to plug in an x value that is larger than 3, you're going to plug that into 5x minus 1, okay? And so now we actually have 4 limit problems. 2 of them are focused on the x value -5, so -5 here and -5 here. The other 2 are focused on +3, which is right here and right here, okay? So this is going to say, this one says, what's the limit of g of x as x approaches -5 from the left? So we're looking for numbers that are smaller than -5. Well, here's -5, and here's where x is smaller than -5. So we're going to plug -5 into this piece right here, and that'll give us the answer. -5 plus 3, that's -2. Therefore, the answer to this limit is -2, okay? But this one says, what's the limit of g of x as x approaches -5 from the right? So now we're dealing with numbers that are larger than -5. Well, larger than -5 is here or here. All of these numbers are larger than -5. But it's supposed to be approaching -5. So it's got to be close to -5, even though it's larger than -5. So that would be this one right here. So here, all these numbers, like -4.99 and -4.999999, those are in this range right here, between -5 and 3. And so we're going to plug -5, because we want the numbers that are larger than -5, we're going to plug them into this one right here. Well, -5 squared, that's +25, because -5 times -5 is +25. Minus 11, that's 14, right? And so the answer to this one is going to be 14. Okay, there we go. All right, now let's come over here. And this one says, what is the limit of g of x as x approaches 3 from the left? Well, this one is related to 3, and this one is also related to 3. But from the left of 3 means less than 3, right? And so because we're looking for ones that are less than 3, we're going to go here. We got x less than 3. So we're going to plug 3 into this one here. Well, 3 squared, that's 9. 9 minus 11, that is -2. And the answer to this one is -2. And now this last one here says, what is the limit of g of x as x approaches 3 from the right side? That means these are numbers that are larger than 3. Well, that's this one here, x larger than 3. So we're going to plug 3 into this one for this particular limit. And 5 times 3, that's 15, minus 1, that's 14. And therefore, these are the answers to all of our one-sided limits based on this piecewise function. I recommend that you watch this section on piecewise functions just a couple times, because there are going to be several questions on the quiz that ask you that are just like this. Now, in my opinion, these are very easy as long as you can decipher what it is you're looking at. So I'm going to put a bunch of these on there. If you have a problem with this, maybe we should meet online and I can help you out. Okay, but that's our beginning to limits and one-sided limits. And in the next set of lessons, we're going to work on two-sided limits.